Hi everyone, thanks for coming. My name is Vojin. I'm working in Oracle Labs in VM Research Group, and I'm a researcher there. And today I will share with you a piece of work that we've been working on for the past couple of years. Oracle Labs has more projects, but this is one of the bigger ones. And the title of the talk today is Polyglot on the JVM with Graal. So before I continue, I unfortunately have to say that all of this doesn't reflect, that I say today doesn't reflect the views of my employer. So, yeah. As you probably know today, there is more than 1,000 programming languages in the world, right? Not most of them are used, but a large portion of them, let's say first 20 programming languages are widely used, and often so they're used within the same project or even within the same basically working unit, kind of the same session that you do. So if you look at GitHub, this is the data we have. You can see that there is currently at GitHub there is 300,000 repositories that just actively work on JavaScript, and then there is a bunch of Java and so on. So there is like a bunch of different repositories. So all of these languages are vibrant, and especially in environments like data science, people kind of work with many different languages, and in research, but also commercial projects. So it's common that basically a project has 2 to 5, 6 languages within it. So the world is basically polyglot. We need to know all these languages, and people use them all around. But what about the performance of these programming languages? Let's take a look at this this graph here. So on the y-axis in this graph is basically the performance normalized to the performance of C programs. This is like a subset of programs. It doesn't really represent well what happens in real life, but it's a good indicator. So and then on the y-axis, on the x-axis, we have the language. So if you look at the languages, we can see that essentially C and C++ are of course fast because they run natively. And then Java and JavaScript, which are the most widely used languages as we've seen, they're quite well optimized. There was big teams working on optimizing these languages. So these languages are about 1.5 to 5x slower, depending on the workload. But then we go to the other programming languages, which are as well widely used, for example, Python or Ruby or R and PHP. And we can see that the performance of these languages is basically very low. So we see slowdowns of between 10 and 400x on your programs. And it's very common that people even write things in R, for example, and then once they want to put it in production, they have to rewrite all the code back in C. So this is one of the problems with this many languages in the world. And let's see why does this happen. So currently, right, when you write your own language, you start with a new language, let's say, and you write a little prototype of it, right? So in your room on the laptop, you quickly hack up a parser, right? The parser parses the syntax trees, and you get the syntax trees that you then interpret and give the meaning to your language, right? And this is a relatively easy process. Students do it in the university all the time, right? So, and then at one point you can get serious about your language and you write a real VM for it, right? So you need to write the garbage collector, the runtime, but you're still using the AST interpreter and it's slow. At that one point, right, people start using your language. So, for example, JavaScript. And then what do you do, right? Then people start complaining. Why is this language slow, right? So what's your obvious step forward? You say, well, we'll rewrite this language from an AST interpreter to a bitcode interpreter, right? And this is what happened to many languages like Python, for example. So this still does a bit faster than the plain bytecode interpreter, but you're not fast enough yet, right? And then people still complain, your language is slow. So what are you going to do now? Well, the only way is, like it's been discovered many times, is to write a JIT compiler and to fix your garbage collector. But here is where the problem lies, is basically at this point is that this is a very costly thing, and not many people have resources to do that, right? So thanks to Google we have V8, right? And thanks to Sun we have Hotspot, but that's really hard and expensive, right? And how we see the world and how it should be is essentially you prototype your new language, you build a syntax tree, an AST interpreter, and your language is fast. That is like what we are striving to achieve. And then the final thing about this approach of building VMs for each language, that when you want to communicate between these languages in any way, whether is it within the project or outside of the project, you essentially need to go with this extra process communication, right? So you have to go either by message passing or by shared memory, and these things are always very expensive and cumbersome, right? So this is what you typically don't want to have in your programs. So, and the final problem that I want to state before I start with what we do is basically the problem of communication with native code. So if any of your languages needs to be embedded into a project, right, it is very hard to do so because the VMs are usually very cumbersome and big. For example, if you would try to put hotspot into some other native project, that would be very hard, right? Hotspot starts for a very long time. It has the warm-up. Communicating when it's heap, it's very hard, right? So essentially, again, you need to go to extra process communication, and this happens in many projects. So you basically, again, get into a position when this is costly and cumbersome. So now that I stated the problems, I'll kind of, just to summarize them. So it's essentially, fast languages are really hard to implement, and therefore even the languages that are used by hundreds of thousands are still slow. Even millions, right? Interoperability between the languages is cumbersome and costly because they're always implemented as different projects, right? And the barrier between languages and native projects is large. So they're rarely integrated together. So in the first part of my talk, I will basically present Graal, which is a compiler that we are building in Oracle Labs. It is, so Graal is essentially, so how many of you know how JIT compilers work? Can you just raise your hand? How hotspot works? Okay, so a slight digression. So when you run your programs in Java, what happens is basically they start running in an interpreter, so they're very slow. And then at one point, when you kind of run them for long enough, you figure out which methods in your program are very important. At this point, a compiler, which is called a JIT compiler or a dynamic compiler, kicks in and starts compiling your frequently optimized methods so that your programs get fast. So basically, the Java hotspot, it's like the Java runtime. Essentially, it has two components. It has the runtime itself, which is the garbage collector and all other components. And then it has a JIT compiler. So what we've done, essentially, to build it has two JIT compilers, actually, a server one and the client one. So what we've done in Oracle Labs to kind of allow us to add another compiler is we build this interface on top of hotspot that allows essentially plugging additional compilers. So now whoever wants to add a new compiler to Java is able to do so without interfering with the hotspot itself. And then we built a Graal compiler, right, that now can run all of the languages that compile to bytecode, such as Java, Scala, or Groovy. So, but the question is, why build a new compiler, right? Well, Graal has certain properties that hotspot compilers don't. So first of all, it's written in Java itself. So the compiler that essentially optimizes your code is written in Java, but before it optimizes your code, it firstly optimizes itself because it's written in Java. So it's kind of self-optimizing compiler, and which is a bit funny, but and then what it does essentially, what does this give you is that essentially when you manipulate ASTs, which is usually a very complex operation, and you have to anyhow like worry about many other things, you basically don't have to worry about memory management. So, and this gives a certain ease of working with the project. Then further, you have all the tools from the Java ecosystem, such as refactoring tools, and this makes it easy to kind of evolve the project easily, right? Then, secondly, Graal has a modular architecture. So anyone can come in and configure the set of phases that are running for your JIT compilation. So you can add, remove phases build your own phases, right? And essentially, it's very easy to work with the compiler, and it also makes each of these phases kind of aware of the environment, because the hotspot compilers are kind of blended together. Here, because of this modularity, you kind of always need to write your code relatively clean. And then it's also designed for speculative optimization. So this means that you can kind of assume some things at the runtime. So for example, that some types are not loaded, or that some values have a certain type, and then you can optimize code based on that. And this gives you huge speedups in certain cases. And then finally, it is designed for exact garbage collection, and it does aggressive high-level optimizations. So let me show you one of these, which we call partial escape analysis. So here we have a function which basically gets a cached car from a cache. It's a really naive piece of code. But I'll show you one of the optimizations that Graal does that no other compilers do. So basically what happens here is we create a new car, and then essentially we kind of look for this car in the cache entry by its horsepower and name, right? And if we find it, we basically fetch the cache entry and return it, right? Or otherwise we add a car to the cache. But here what is interesting about this code is that every time you call it, you have to create this object car, which is very costly. So what you want to do is to kind of get rid of these allocations as much as possible. So what you can notice here is that some paths in this code are very unlikely. So for example, if we have this else branch, which adds a new car to the cache, that one will be seldomly hit, right? So, and we can notice that the new car escapes only in 2 places out of this method. So for example, here and the add to cache, and basically when you return. So what we can do is we can move this allocation here inside of the else branch, which is less frequent. And then here we can just use directly the values that are passed in. So we essentially remove the allocation from the hot path, right? And in some benchmark, essentially with streams, this gives you huge performance improvements. So, and then we have many other optimizations, but let me show you the performance of Graal on some examples. So here I have this program, which is essentially using Java streams. You see this well? Yeah. And then in this program, we can see that we have, essentially we have a loop that iterates over a bunch of, iterates 30 times, and then it does so it does a same operation many times in order to kind of warm up the code. And then it calls this function getValue, right? And of course, in the end, it reports the time, right? So, and then it calls this function getValue, which essentially takes a stream of persons that we have, and then filters them by gender and height, takes their age, and takes all the people that are bigger than that are older than 10 years, takes their average age, and gets this value, right? So it evokes many stream operations. So when we basically try to run this code, right? So let's compile it. Let's see what happens with Java, right? So first iteration is like basically in the interpreter, so you see that it's slower, but as the compiler compiles more and more of the code, you see that the code is speeding up, right? And we get a faster version in the end. However, now let's see, so the one iteration runs 240 milliseconds. Let's now run this with Graal. So this run just hides a bunch of options that I wanted to show you. So didn't want to show you. So you see that Graal starts very slow because it's written in Java. So the compiler itself, it takes time until it warms itself up. But then it basically gets up to 34 milliseconds, which is 5 or 6 times faster than what Hotspot would do. And what's interesting, what happens in this benchmark is basically that Graal has a very sophisticated inliner, which kind of does a cost-benefit analysis. And the inliner will realize that by inlining arrays.stream and all of these functions, right, that the arrays.stream has a loop inside which can be statically known and unrolled, so it will in the end basically get one single while loop which will execute these predicates, right? So all of the overhead that is around will be removed, right? So a simplified version of such loop, what happens here, what's inside, what the Graal will see is basically, it will see this while loop of the array A, but of this array, the length is known statically, right? So basically because this length is the number of functions you invoke here. So this loop can be then unrolled and all of these internal operations can be fused, right? So that's why essentially we get such speedups. So, back to the presentation. So, and because of its flexibility, it's kind of easy to experiment with such optimizations and add new ones, right? So, and then because it's written in Java, it's also easy to build things on top of Graal, because interfacing with compilers is usually a very complicated task, right? Compilers move very fast, and if you try to interface directly with them, it's very complicated. So what our team has built is this framework called Truffle, which is kind of a very nice interface on top of Graal that uses partial evaluation to basically express what you want to do, right, with your languages. So, and then this framework makes it easy to build languages on top of Graal, which don't use bytecode, but rather just use the Truffle APIs. And we've built a few languages on top, Ruby, R, JavaScript, and a few others. So, how does Truffle work? It is an AST interpreter, just what we wanted in the second slide. We said we just want to write an interpreter, but it has additional annotations that you specify with the DSL. And basically, what do they essentially do? Is that you run your code in the AST interpreter, and as you can see here, all the nodes are in the beginning basically uninitialized, so you kind of don't know anything about them. It's just the interpreter, the slowest version, right? But then what Truffle will start doing is it will start tracking types in nodes, right? So if, for example, if you have a plus operation in JavaScript, this plus can be a plus of strings, it can be a plus of doubles, it can be a plus of ints, right? So what the Graal will do, or what Truffle will do, it will track what was the previous values, and if it was, for example, always int, it will mark this node as int, right? And then, but then later it can, of course, transition into a double if a double appears, right? And finally, it can be a generic node which will do a check. It will have to check every time. Is this a string? If it's a string, do a string addition. If it's an int, do an int addition, right? And then we build this graph of specialized nodes, and then we start partial evaluation. So you basically fuse all the nodes of this graph in one big blob of code, which is essentially assembly. And that's it. You get your fast code. And then what happens if, for example, you had an assumption that something is an int, but then a string comes or a double comes? In this case, a double. Well, you de-optimize back. You say, I'm going back to my interpreter. Let's see what I'm getting. And you say, aha, this was wrong, so I'm getting doubles here. Let me re-specialize and then produce a new piece of assembly. Okay. So let's see how effective this is in practice. So this is code in Ruby, which essentially does a very simple sum. So we have an addition function, and we have a while loop that adds until n. So when you look at the assembly that gets produced after running this function, so you will see a very simple thing. You will see basically addition, right? This is compared to add. Then this JO. Does anyone know what does JO do? Okay, so this is just a single instruction which will check basically, did this overflow? Is this still correct, right? And it will basically jump out and de-optimize. But this is very cheap for the processor to execute because it's always known what it does. And then it will basically just jump back after the comparison. And you can see that also all of the values are in registers, right? So the register allocations has removed all the variables and all the stuff. So you get the loop basically the same that you would get in C, except of this JO. But these assumption checks are usually very fast because the branch prediction hits them every time. So they are basically just swallowed by the CPU. So Yeah. Okay, and then on top of Truffle, what is the problem with this approach is that essentially it's easy to specify the languages themselves, but the languages already, because they were written as an AST interpreter or a bitcode interpreter, they started making hacks to make themselves faster. So, for example, Python and Ruby, they use a bunch of C written code inside them to make things go fast. And then it's kind of a patch of bytecode and the assembly. So what we did is this project Sulong, which is a recent effort. And the Sulong basically on top of Truffle puts also LLVM, so that you can integrate all the LLVM code that you get. So essentially, how it works is you basically just, if you have a language that uses Sulong, anything that compiles to LLVM, so C++, C, or Fortran, and so on, you can basically Rust. You can basically take this and compile it into LLVM, and then just run it with Truffle and get, again, fast code, right? So, and let's look at the performance numbers. What we get with this whole effort, right? So this is a lot of work went into. So for Java, we basically get a slightly better performance on this is like an average over many benchmarks that are common in the community for each, right? So for Java, for Scala, for Ruby, and so on. So essentially, for Java, what we do is we are just a bit faster than the hotspot currently is. For Scala, however, which uses many abstractions, essentially Graal gives 1.2 performance speedup, which is already significant. And then for Ruby and for R, you get basically 4 to 5 times speedups, which is nice. And then for Sulong, the native part, we are of course slower, right? Because if you compile something with LLVM will certainly do a better job than you putting this on the JVM, which has managed memory. But still, 0.85 is quite good. So the C code you run will be relatively fast. And JavaScript is 0.9 because V8 is a super optimized hand-tuned piece of code for JavaScript. But this is still a very good result. And then the completeness of languages that we have essentially is about 99%. So Ruby language 99%, JRuby passes 94% of the tests, Ruby core 96, ECMAScript in 2015 is like 99, and only Unicode regular expressions are missing. Basically, people should just add them, and there is no fundamental reasons this is not 100%. And then ECMAScript 2016 is 91%. So basically, the languages are basically being released very soon. And just to show you how, in practice, how this works, let's go to, let's take this R program here, which basically just does a simple sum. It's a for loop, and it makes a sum. So let's basically run this program in R. So if you say sum of, I don't know, 100, let's do it's very fast, right? It runs in 0 seconds, right? But then let's do a sum of 1,000,000, for example, which will still be very fast. And you can see that it's already 0.2 seconds, right? Let's do up to 100 million, for example, in R, and you know, things get bad, right? Because this is R. It is interpreted and it runs very slow for certain things. So, and yeah, this basically will take a while. Okay, and then let's stop it. And then let's take the Graal VM shell. Graal VM shell has multiple languages, so let's change our language to R, and let's make this function. And then let's try a sum of 0.4 seconds for 100 million, right? And then if you run this sum, it will probably get faster and faster, right? Because compilation, as you compile more and more, right, you essentially get 0.01 seconds, while R was still running, it was at least 10 seconds and more, right? So this is essentially this type of speed up you get. The only thing is that warm up, you need to kind of run your programs for a while until everything gets compiled. Okay, so what we've done by now is essentially we kind of made it easy to build languages. Just this little summary, we made it easy to build languages. We kind of provided speedups over bytecode based languages. And then we also supported like C++ based languages. So this brings up immediately, why not just mix them all together, right? Because now we have all the languages. So the native languages like C++ and the dynamic languages like JavaScript, we have them in the same VM. So let's try to mix it, right? And just before I continue, I want to ask you one thing. So how many times did you go into a programming language just because it has a library? So did you ever go into a programming language just because of a library? If you did, like, raise a hand. So you never took out Python just because it has good libraries, or R because it has statistics, right? Okay. And in 2013, at Berkeley and Princeton, they did this study, which is published at Uppsala, which essentially says that people care about libraries, right? So when you choose your language, you will choose essentially the one that has the best libraries for you. So when they asked people on their projects, how did they choose the language, they said that 80% of people basically said that it's medium or high importance for them to have the open source libraries, and then they will choose the language based on libraries. So, and this is particularly visible in data science, where libraries are kind of all around. Best natural language processing is in Java, the best numerical libraries are in Python, some are in R, right? So people just like write all kinds of scripts and then connect them with Bash to get the final pipeline that they want, right? So essentially, and we are so used to this that we never thought this shouldn't exist, right? There shouldn't be barriers between languages. And that's why we do essentially something like this. And what we want is basically to put all of the languages in a single VM. But not only put them in a single VM, is put their implementations that they know about each other, so that essentially the interoperability between languages costs 0. So how do we do this? We basically, for now, it's a starting, I mean, the project is relatively new, or maybe a year or so. We basically provide something called interop, where we can, in each language, evaluate source, right? And then we can import names and export names into interop. So you can basically, from JavaScript, you can export functions, or from R, you can export functions, and you can import them and run them in a different language, right? So let's try this in practice, how this works. Okay. So let's first look at this Hello Polyglot program. Essentially here, we have Hello Polyglot world in Java, and then we spawn something called a Polyglot engine. That's the main engine for running languages, right? And then we say, well, let's print something in JavaScript. Here's the string for doing that. Then say, well, let's print hello world from Ruby, and then do, make a random distribution of 100 numbers in R. So uniform distribution. So, and then what we say is engine, evaluate, that's what we've seen before, right? And then you say source and JavaScript, and then pass all these things, right? So let's run this program. So Hello Polyglot Java, JavaScript, Ruby. and R, right? So all of the languages in the same VM. So now I prepared this also for calling functions. I prepared kind of a cookbook. So you can also enter the shell of this Graal VM here. So, and you see that in the shell you can change between languages, right? So this is essentially built, this is basically built on top of the functionality we've shown. So let's take some programs. So let's first in R define a timing function, and then make some big array and try to work with this. Right? Sorry, this shouldn't be here. Let's do that. Oh, this is an error, not in Ruby. Let's switch to R. Okay, so now we have a function called time that we can call over, for example, this built-in sum of a vector. Let's try. Sorry. Unfortunately, it loaded the previous session, so I will not be able to show you this demo. Yeah, I'll have to skip this demo, unfortunately. But essentially, because I had the other R session that got polluted. So if time permits, I'll do it in the end. So basically, but essentially what you can do is you can call different functions from different languages, right? So you can call JavaScript functions from R, and sometimes it's even faster, right? So basically, if you call a JavaScript addition, it's faster than the R addition because it has a slightly different semantics inside, okay? And then finally, the last thing I want to talk about is this barrier between the memory managed code and native code. So essentially what we had before, what we want is to be able to embed all our languages inside of a single, inside of any native project. And in order to achieve this, we built a VM, which is essentially called substrate VM, and it's an embeddable VM for Java, and it's also written in Java. So the whole VM is written in Java, but it compiles down to native code. So all of the Java is, instead of JIT compiled, it's ahead of time compiled into native code using Graal as well. It is integrated with native development tools, so you can use GDB and all other tools for it, right, for debugging. And then finally, it's optimized to execute all of the Truffle languages. So what does substrate VM do? It is essentially, you take all the languages that you have, so all the interpreters, you take the JDK, the Graal compiler, right, all of that, and the substrate VM itself that is written in Java. So you take a garbage collector and so on. You do points to analysis on top of it, right? So you kind of try to find which methods out of all of these methods are reachable and essentially needed for your executable. Then you also check for fields, classes. You execute static fields in order to get the state. What is particularly neat is that you can kind of specify the point and the amount of things that you can put in your, that you can pre-initialize kind of and store into your image. And what you finally do is you produce a binary which has an initial heap, all the info required for running it on a certain platform, and essentially machine code, right? So there is no bytecode whatsoever. All you get is assembly. And you can get two types of assemblies. Ones are shared libraries, and the other ones are basically just the executable. So you run it as normal programs, right? So we can do an example of such a thing. So if we do here, we will basically invoke this command that runs an image, and if you see here, it makes a shared library out of JavaScript. So, and this shared library, what it will do is, if you run this compilation, you will see that it starts analyzing the classes, setup, starts doing analysis, and this will take a while. It takes about 50 seconds on my laptop or so. So I'll let it running, building this shared library that contains the JavaScript language within it. So what's nice about Substrate VM? So first of all, it has a very reduced runtime, so it's not as big as Hotspot. It's very easy to start. So essentially, all of the things, including the heap, which is chunked, so it's not a contiguous big heap, but it's kind of made of small pieces, is made that it's easy to kind of embed this VM into your code. And then it also basically uses something we call system Java for integrating with C code. So I would also like to look at this. All right, so system Java is basically, it's similar to JNI, but it has certain differences. So it is used basically for integrating with legacy C code. So for example, if you have something in libc or any other code that you want to use, you can call it directly from your Java programs. But essentially, what you do is you don't pass the, okay, I'll explain this first. And then essentially, you also need system Java to call, you also need a functionality of it to call Java from C, right? So if you want to embed your VM, you want to be able to kind of call the things you've written in system Java from C itself. So let's, what's the difference between JNI is that essentially in JNI, you kind of, you give the objects to the C code and you give the handles, and then the C code needs to kind of work with Java objects in order to convert them to something representable in C. And what system Java is essentially just a set of annotations that we provided that you can write directly C code in Java. So it's, there is no passing objects to C and then you have to kind of handle them in C. No, C stays C, you pass structs to C, you pass pointers to C, and that's it. Right? And all you need for this is essentially a word type for low-level memory access. So essentially, we support accessing it through Word, so because it can be 34-bit or 64-bit, and then you have the base interface words, and then you have its subclasses, which are pointer, unside, and side for type safety. Right? And if you look at here, for example, string len written in system Java, how it looks is we say word 0, and then we say read a string, which is a char pointer, as you would put a star char in C. And then essentially until this is different than 0, which is the string terminator in C, right? You add 1 to basically your sum and return n. So, and this is C code, right? So it's just written in Java. And then if we go a bit deeper, right? So what we can do is we can reference existing C functions with this add C function annotation. We use also native so that we don't have to specify the body. So we can call clock get time, basically. We can define constants, which are in this case defined as methods, right? We get it like this. We can define interfaces, which are used as structs. So when you work with them, you basically, in Java, you feel them like interfaces. You can do all kinds of nice things on them, but they're basically transformed into accesses into structs. Right? So what the Graal compiler will do when it sees a C struct, it will kind of look into the offset of the struct in C, and then it will kind of change the memory access to this field to be according to this struct. And so on. You can do, say, C libraries, which is linking a library. You can import stuff from C libraries. And then if you look at, for example, nanotime, how we implemented in system Java, we'll basically call C stuff, right? Because now you're embedded into a native project, so what you need to do is say stack value.get, and then you say time spec, right, size of, the same as you would do in C. So this allocates on stack. You don't even have to free it, right? And then essentially you say clock get time, and you pass this as a pointer. And finally you do math, which you return back. And this is how we do long nanotime. So what does this give you, right? So first, let's see if our image is complete. Yeah, here it is, right? So it compiled 5,000 methods for the optimization. The analysis took 20 seconds, right? And in total, this image, if you look at it, the whole JavaScript, right? Sorry, we didn't build JavaScript, we built a library. Here we are. It's a dynamic library, 61 megabytes. So we made a dynamic library that we can link here with 61 megabytes. But I prepared another image, which is basically, this image is with special flags. So I call it JS alloc profiling, just to show how lightweight it is. So when we call this, when we call so this is a JavaScript shell, so you can do all the JavaScript stuff, right? And then we say exit. Let's exit this shell. It will print in the end, because it was built with special flags, it will print how much memory it consumed. So starting the whole JavaScript VM, it took 107 kilobytes of memory and allocated 1,530 objects. Yeah. So this is basically nothing, right? Just for starting the whole JavaScript. And then also where this also pays off a lot is in startup performance, because as you've seen with R, when we were running this script, it was basically taking a lot of time until it warms up, because Hotspot needs to warm up the Graal compiler first, and then it warms up, it compiles the methods, right? So in this little benchmark here, we wrote a micro benchmark, which will essentially just go over objects and sum them up, right? So it's a very, very basic thing. But what you can see here is what happens when you run it. And here on the x-axis, we have iterations, 0 to 10, and then 0 to 200, and 0 to 40,000. And we have Google V8 different, these are not important here, and we have Truffle on Hotspot and Truffle on Substrate VM. These two are important. So what we can see on the first 4 iterations already of this benchmark, essentially, you know, the execution time was growing, but then it stopped because the compilation was done only after 4 iterations. However, on Hotspot, what happens is like you need up to 100 or even more. It still compiles, right? 100, 200 iterations. And then when you look in the end, right, they kind of run the same speed, except that Hotspot has this initial 2-second startup overhead. And this is why in Substrate VM, for example, if you would like to use Ruby that's built on Truffle, if you would like to write scripting languages, like use it in scripts, for each script you run, you would have to wait 2 seconds. And that's not really acceptable. So, yeah, and here we also see the memory footprint growing when the compilation happens. Right? Yeah, so let's just look at how we can embed this VM. So we built this shared library here in this tab. Yeah, so we essentially here, we built a library. So it's a dynamic library. So what we want to, and then what essentially, yeah, so let's start like this. So essentially, I got this, in this demo, I got this data, right? And this data hides something in it. It kind of looks the same size, but it has a message in it that's longer, right? But because I'm a JavaScript programmer, and I don't know how to essentially use sed, with grep, I cannot find this, right? Because grep just finds regular expressions, but doesn't find the lengths of strings so easily. So I'm a JavaScript programmer, and I don't know how to do it. So I decided to build grep.js in order to achieve this task. So let's look at our essentially grep.js. So I took Truffle, and I heard Truffle is cool, and it runs node.js on top of it, right? So basically, I defined this node grep.js, which basically will, you know, read the file. It's a very basic grep.js. And it will essentially run a filter function that you pass to it on the data, right? And it will read each line of the data here and run the function. And if this filter is correct, it will basically return the console.log. It will print that line. So let's run this. So I made a script for this, which is grep.js. And then we want now, instead of passing a regular expression, we'll just pass it a JavaScript expression. And the line is called L, so we want a length of line that is, I think, bigger than 9. I think this was the case, right? So, and then we say from the file, which is called data. Okay. And let's see. Oh, well, that was the startup time. Oh, it wasn't 9. Let's try again. So 10. Right? So, and look how much time you need to wait for each command to execute, because hotspot starts, right? And then, oh, we found the thing. So Joker is an awesome conference. Sadly, I don't understand Russian. On the bright side, there are good English talks. So, but when we try to time this, essentially it takes 2 seconds, right? So, and now because I want to make my first .js library, so I decided to build a grep.js in substrate VM. I heard this library can make it faster. So, and then what we did here is we already built the library. And then if you look at the code, let me show you how integration works with system Java. So here we have grep.js.c, okay? Sorry. So in grep.js.c, this is a bit of, so what all we need to do is essentially invoke this function, which is external run JavaScript, right? And then we implement a bit of grep, a very rudimentary grep, and what we do is essentially we run JavaScript with a filtering function here. You don't have to look at the details. But this is how easy it is basically to integrate the whole VM into your program, right? And then what you want to do, right, is essentially just link it. So this is done with GCC, right? So you say essentially build my grep.js.c and link it with the library, which is called also grep.js. No, it's called run JavaScript, right? So this is the library that exposes the function. And linking is done, and that's how you get the binary. So if you look at now how this runs, so let's first look at the Java version, right? So this was the C version calling Java, and then I also have here JavaScript runner.java. It's just a simple Java class which says extern C. This means export this as a shared function and call it run JavaScript. This is what we were calling. And then what we need to do is convert the char pointer from basically string to Java. So we call this substrate util to Java string. They have different encodings. So this is what you would, in JNI, you would have to write these kinds of things in C, right? Here you write it in Java. And then finally, let's just invoke it and return an int. So it's as easy as that. Say just VM and eval, right? And this is it, right? So we joined these two programs, and we got our grep.js, which is based on SVM. So let's try the same thing. And let's time it. It's 0.2 seconds to execute the same thing. And yeah, so that's basically what you get with this, with the whole stack is, the possibility to essentially first run all the languages fast. This is the picture now of the whole stack. And so languages go to Truffle, and then they have different VMs, a substrate VM or Graal VM. So you can implement your languages easily. Languages run fast. They talk to each other. So basically all the libraries from all the languages become available for you. And then finally you can run it basically inside of the native code, embed it in any VM. So if you have a load balancer or if you have a database with UDFs, your UDFs just put in a library and your UDFs can run all the languages, right? And yeah, so that's more or less it. So it's fast and easy to implement languages. Yeah. So many of this effort is open source, which is really cool, because when you kind of work for a company like Oracle, that's not often the case. So the whole Graal VM is open source. The Graal core compiler, most of the compiler is on GitHub. Truffle as well, FastR, Sulong, which is the LLVM, Ruby Truffle, and the simple language, which is our example language. They're all open source. If you want to learn more about these technologies, you basically can go to Graal and Truffle tutorials. You have them at this. You have them on this link. And this was done by many people. So this is just the list. And it's basically a collaboration between Oracle Labs, which is this list. It's led by Thomas Wertinger, and then there was a bunch of interns working on it. And there is also a lot of university collaborations, right? And also, if you would like to be on this list, we are currently hiring. So essentially, we are always looking for great students to be our interns, or a bit more experienced people to be employees. And essentially, we have a bunch of locations. So in the US, Austria, and possibly in St. Petersburg soon. So this is about it. If you have any questions, I'm looking forward to answering.
Thanks for the great talk, but I want to know, this product was created to replace some other product of, suppose Oracle, I don't know, compiler or maybe VM, or just additional product like it was created for Maxine VM, as I remember?
It's an additional thing. It's not meant to replace anything. It's just an additional thing which gives things that the previous approach is an amazing work, right? There is no question. There is no intent to replace it whatsoever. This is just an additional thing which is growing in Oracle, right? Yeah.
Actually, I have one.
Yes?
Does it support Kotlin or Scala?
Scala it supports because it's a bytecode language, right? And it compiles to bytecode. And for Scala, it's faster than the hotspot VM. And it's also, since Java 9, the JVMCI is basically scheduled for Java 9, so you'll be able to run there on a hotspot you download, right? For now, we have to modify it for Java 8, but for Java 9, you will be able to run it. And for Kotlin, I think Kotlin also compiles to bytecode, if I'm not mistaken. So basically Kotlin as well. Yeah. So okay. I just didn't put it in the list. It's essentially all the bytecode languages are supported. Python is unfortunately not yet supported, but there are plans to do that as well.